Hello, my name is Peter Warren, and I am a graduate student at the University of Central Florida, currently pursuing a PhD in mechanical engineering. My advisor is Dr. Rana J. Ghosh, and I'm going to give a quick presentation today on a paper that I just wrote, and we're going to be submitting it to a journal pretty soon. The paper is titled Artificial Grain Boundary Generation from Voronoi Tessalation Patterns. The interesting thing about this work is it's not just purely artificial grain boundary generation. The purpose of this work is to obtain better methods for measuring grains, quantifying grains, and just the utilization of machine learning and artificial intelligence-based approaches to obtaining accurate grain information. So the layout of the presentation is as follows. I'll start with an introduction on and explain grains and grain boundaries, why they're important. Then I'll go over some image segmentation techniques. Then I'll talk about grain measurement and accuracy, the different types of grain measurement, and how to quantify the accuracy of those grain measurements. Then I'll get to the heart of this work, which is the artificially generated grains, or the Voronoi grain generation technique. And then I'll explain the machine learning methods used in this work, which is basically just convolutional neural networks. We'll go over the results, whether that's dice score, the grain data, or even some qualitative results as well, and then some conclusions I can draw from this work. So stainless steel is one example of a metal, and currently there's a lot of work being done and new and innovative manufacturing techniques of stainless steel, mainly additive manufacturing. I have a few examples of what images, microscopic images of stainless steel might look like, whether that's SEM or optical. And we can see that the different types of stainless steel produce, the different types of additive manufacturing produce a different microstructure of stainless steel. So in order to further develop these additive manufacturing methods, accurate grain measurements can help to benefit these new and innovative methods, whether that's BJT, which is binder jetting, SLS, selective laser sintering, FFF, the Mark Forged Metal X, fused filament fabrication. And these two are the same here. We have a BJT from the X1 print, and this is optical versus SEM. And this is one of the samples used in this work to create the data set that was used in this work. And this one was polished and also prepared using etchants, and so it was etched properly, so we have a nice grain boundary. It looked like it came out very well with the optical microscope. The SEM not as well, but perhaps the settings could have been further tuned to get a better image there. So mainly we ended up using this optical microscopic images. This is at 500x. So I'll continue to explain that later in the work. But just quickly, the benefits of accurate grain measurements are you can get a direct relationship with material mechanical properties. So therefore, you could optimize those mechanical properties or optimize additive manufacturing processes, mainly the sintering stages. So some of these, the BJT and the FFF, both have a sintering stage that they go through. So you can optimize that sintering stage if you have good grain measurements. And also grains can provide the ability to create multi-scale models of a given material. So just a better overall knowledge of a material can be obtained from accurate grain measurements. But there are challenges to obtaining accurate grain measurements that we found during this work and are well established. Polishing, etching, and imaging. Those are three challenges right there. First, we have to polish the sample and etch it, and the different etchants produce different results. The amount of time you leave it on there, it's a very complex process, and the right recipe can be difficult to obtain. Imaging is also a problem whether you're getting your images from SEM or optical. That can be challenges. And then, but say you do get step one done pretty well, and you get a nice image like the one shown here. Next, you have to classify your grain boundaries. If you're going to use a computational method, you need to classify your grain boundaries from your grains, and then classifying scratches and pores and impurities, and kind of deleting those from and not classifying them as grains. So it's the next difficult step would be taking this image and classifying each pixel as either a grain or a grain boundary. And these pores here, well, the next slide will explain this better. So here we have an example of one of the images from this work. This is stainless steel printed on a BJT printer. But the main portion of this work is just directed at the image and how do we classify grain from grain boundaries. Here we have the grains, and then here we have the grain boundaries. So if we can classify that, then we can get accurate measurements. We don't want to count a pore or an impurity shown here as a grain boundary, and we don't want to count a polishing scratch as a grain boundary either. So the polishing scratches are a very big challenge. Maybe a better polishing method or more care taken during the polishing stage would have made this challenge easier. We did take great care though as we polished it, and still have some polishing scratches that occur throughout this material. Also, small grain fragments, we don't want those to count as a full grain and throw off the measurements. So that's essentially the problem statement of this work. Classify each pixel as either a grain or a grain boundary. So now let's talk about 4 traditional segmentation methods. Maybe more could be added, but for this work I found these to be the main and the best approaches to classifying pixels as grains or grain boundaries. And I have them shown at the bottom here if they were applied to this image of a lion. So there's manual thresholding. There's a gradient-based approach, which is shown here. Manual thresholding is shown here. And the HED method is a machine learning-based approach. It's a holistically nested edge detection. It's basically a neural network that is very capable of detecting edges of an image, whatever that image is. And the results from that are shown right here. And then manual segmentation would be if we opened Paint or whatever type of software and manually annotated the boundaries of this image, however you would want to do that. If you manually annotate it and sketch it on there, then you can control which boundaries you want to mark and which boundaries you do not want to mark. So let's go through those 4 main methods and show them to this grain image here, and just a quick step-by-step approach if someone was going to code this. I do want to make a video later on getting into the actual code of this stuff, but for this I'll give it more of an overview of what's happening from the code's perspective. So first we have the original image. We convert that to black and white. You can take a histogram of the pixels, and then typically you want it to be applied somewhere. The 0 here is indicative of black pixels, and 255 would be purely white pixels. So we want all the pixels below this red line to go to black, all of them above to go to 255. So it's up to the user's choice where to draw this red line. There are some adaptive thresholding methods as well, where it goes based on whatever pixels are nearby, but you know, for the most part, you're going to pick a line and segment all the pixels to white or black based on that line. You could do it from the average or just before this peak. So this peak is all black pixels. All of these grain boundaries, polishing scratches, and pores are all included in that. Beneath that is the grains themselves. These pixels are closer to the white value. Or sorry, above this area is the grains, and this area would be grain boundaries. Closer to white, closer to black. We can apply a standard threshold seen here or an adaptive threshold seen here. We can do a median blur 4 iterations and clean it up a little bit more. And then the final result And a medium blur, by the way, just takes a small kernel of pixels, maybe 15 by 15 or 5 by 5, however big you want it to apply, and blurs those pixels using just basic, algebraic or linear algebra terms. Then we can segment those pixels into different grains, and you can see how it doesn't do a completely perfect job, but it does a pretty good job. And then you can filter out this data based on whatever requirements you may have of it. Smaller ones get filtered out. Too large of one might get filtered out. So based on what filters I had in place, the green ones were good grains and the red ones were bad grains and filtered out. Another approach is the gradient-based approach. You can just take your image, convert it to black and white, do a canny edge detector. You can blur it using Gaussian blur method or a medium blur method, 2 iterations, however many. In this case, it was done 2 iterations, and then apply the standard threshold again, which is just the average value of the pixels, or a value that you can test it out and see which one works best. Now we segmented them, so we take all the different ones and segment them into their own grain. And here we can see that we have a lot of red that gets filtered out. That just means that they're too small, or the perimeter is too large compared to the area, so it's not a good measurement of grains. We still get a good measurement overall of the different grains here, but we're missing a lot of key data, and it looks very much less clean than the previous method. Next is holistically nested edge detection. So now we're getting into a good neural network based approach, good machine learning based approach. You just take your black and white image, feed it directly into a holistically nested edge detection neural net. Then you can apply an adaptive Gaussian threshold, or you could just pick a standard threshold, and you can segment the images. And here we get a nice clean image. A lot of good grain data coming from the HED method. Okay, so here we have an example of some manual segmentation of grains. The green is, the lime green here indicates grain boundary, and everything else is a grain, essentially. It is easy to skip over the polishing scratches, the pores, to not draw a grain boundary around a grain that is potentially too small and just small fragments of a grain. So this approach is probably the best approach, but it is also takes a long time. This is performed by a human using manual annotation. In this case, it was just performed in paint. So pretty simple approach. Draw them and then threshold it, and then you can segment it computationally, and you get a lot of good, clean data for the grains if you perform your segmentation manually. Okay, so here we have our data set. I'll quickly explain how we constructed our data set here. There are 480 total images in our data set. They're all from the same batch of printing, different samples, but the same batch. They were printed on a BJT printer X1. They are stainless steel 316L samples. They were taken, the optical images were taken at 250x on an optical microscope. They are polished and etched using the method that we used. That'll be available in the paper. I believe it was just Fry's etchant, or maybe Marble's etchant, available online and used in a standard method. And polishing, of course, just slowly increase the grit, do it slow, and then just standard polishing and etching of stainless steel. The good thing is that this data set is published on Kaggle, as is all of the different there's code available for all of the different thresholding methods. The manually segmented images, all 480 were manually segmented, so that provides a good data set to implement machine learning based approaches for grain boundary segmentation. And it is a good contribution to the data science community. To publish data is very important moving forward for material scientists to better implement all of these machine learning methods. and everyone can kind of benefit from that. So it's something I think everyone should practice. The way that we are going to quantify the accuracy of the grains, and this will be utilizing the manually thresholded grains as a baseline, we'll quantify the accuracy from just standard grain intercept methods or grain measurement methods such as the grain intercept and the planimetric method. And also we'll look at machine learning based accuracy methods, which is pixel classification accuracy. So just the straight accuracy of that, one-to-one accuracy, and also the dice score. So for the grain intercept method, this is kind of just a method to give people a baseline of how large their grain is. It's a somewhat outdated method, but it's also quite quick, so it still is utilized, but typically someone will draw a straight line across, 5 or 6 straight lines, count the number of grains that are in contact with that line, and then divide it by the total length of the line, and that gives you a basic accuracy, a basic size of the grain in the X direction and in the Y direction, and different directions would be important for printing, additive manufacturing in the future. But it's just a quick method, typically performed by hand. But in this case, I did write a code that would do it for every individual pixel line, so that provides even more data for the grain measurements. And these were the results for the 4 what I refer to as the traditional methods. The manual threshold, the gradient method, the HED method, and manual segmentation. We can see that HED did score the closest to the manual segmentation, and manual threshold and gradient method. This one was pretty close as well. Manual threshold, gradient method way underestimated the size of the grains compared to manual segmentation, as shown here. For the next measurements, we'll look at the more accurate, or not necessarily more accurate, but more data-driven approach, which is planimetric, a 2D dimensional method. And we'll look at, again, the 4 traditional methods of grain segmentation. First, from the entirety of the data set, how many grains did it count from all 480 images, I think it was. The manual had 9,500. The gradient method way overcounted at 24,000. HED method 15,000, and the manual segmentation method at 11,000. We can see the individual grain area since we're looking at this from a 2D based approach. And again, for all of the grains, that's what we get there. The one big discrepancy we see here is using these 3 traditional methods, manual threshold, gradient method, and HED method. It's about a 50-50 split of grain area percentage to grain boundary area percentage. But using the manual segmentation method, we get a lot more grain area versus grain boundary. So that means that all of these methods are undercounting the amount of potential grain area. That's because they're classifying all the polishing scratches, all of the defects within each grain as a grain boundary. But that's important to note because that's a lot of data that we're missing out on using these traditional approaches. So here's some more measurements that we can get from planimetric 2D methods, and that is circularity. The formula for circularity is right here, 4 pi a over p squared. The average max diameter, the average x diameter, the average y diameter, and then the aspect ratio. In this case, for this work, it's BJT printer, so the grain boundaries are mostly equiaxed. They are not elongated in either the x or y direction, so there's not big differences in the aspect ratio. They're all right around 1. Not a lot of conclusions you can draw from getting all this data, but for other methods, it's certainly possible that there would be more, so that is a little bit more difficult to quantify if the additive manufacturing method has elongated grains in a specific direction. That can provide a lot of data if you took these measurements for one of those. But I still took them anyway and still wrote the code, and it's all available on Kaggle and online as well. I'll provide all the links in the description for this video. So now let's get into the heart of this presentation, which is the Voronoi Tessalation, which is a method of artificially generating grains. Quickly, on the right and left hand side, we see a nice little mosaic looking pattern. This is formed through Voronoi Tessalation patterns. Essentially, you plot some random points using this code here, and then you can create a Voronoi Tessalation, which just draws the furthest possible distance from each point to create boundaries between the points. So this is the result of a Voronoi Tessalation pattern around randomly generated points. So how can we make grains from that? Well, first you do a Voronoi Tessalation, then you could draw pores and scratches on that, randomly generated dots at random sizes, randomly generated lines at random locations, and here's the final image here. Gaussian noise applied to the background to show grain color. So here we have the original mask. This is what we want to predict. And then set 1, set 2, set 3. So this is just different methods of generating a messy Voronoi Tessalation grain. You can see that it would be very difficult to go from this image back to the original mask. But it is possible. And a neural network can be trained to do that. And it basically, by performing these blur methods and adding in a bunch of pores, it kind of trains a neural network to be able to identify a grain boundary through the challenges of pores and scratches and through the challenges of perhaps a more blurry image. So here are all of the data for the different sets, whether that's how many single black pixels were put into each image, how many larger black dots were put into each image, the Gaussian noise applied to show the grain color, how it was an erosion kernel applied, was a Gaussian blur applied, was a medium blur applied, and then was there 10 random scratches. For each one there was 10 random scratches. So in some cases the random scratch might not be present, but a total of 10 were put on the sample. Some of them might not be directly on it. So that's just how the data was generated for using the Voronoi Tessalation grain generation method. The machine learning based approach used in this work is just a standard UNet. No ResNet, no fancier, newer architectures for a convolutional neural network were used. Just a standard UNet because we wanted it to be a baseline for the different data sets we used to train. So let's look at our training data. That's the more critical portion. Training set 1, 100% of it is manual segmentations. So on the left-hand side shown here, we have the key for the data used. We have Voronoi Tessalation generated grains, so that's the artificial grain generation method. In blue, and with the grain image as the background, we can see manual segmentation. And then also, the 3 traditional methods may not be useful after the development of machine learning based approaches, but introducing the noise generated from those methods into the training set could potentially help to allow a neural network or a convolutional neural network to be more robust against noise that may be in the image. So for training sets 6 through 10, a little bit of noise generated through HED method, gradient based approach method, and the manual thresholding method were also introduced into the training data to allow the network to train against that data and become more robust against the noise that could be generated from that data. Noise is meaning the pixels classified as grain boundaries when they are in fact not grain boundaries and should be classified as a grain. And still, 50% of each of those was trained on the manually segmented grains. So it will be interesting to see what scores these get from a dice score perspective and from a grain measurement perspective. So for the dice scores, which is basically just pixel classification score, and it is a very common score used in machine learning when talking about pixel classification. Manually segmented scores 100% because it is used as our baseline, it is used as our ground truth. Manual threshold actually did the best at 56.47%. Gradient-based approach got 40%, and the HED method actually did the worst. So that's not necessarily a good indicator of how well the HED method did, because the HED method scored the best on the actual grain measurements, but then scores the worst on the dice score. So it's important to look at both of these accuracy quantification methods and look at it from with a machine learning scientist's hat on and a material science hat on. And so when you're looking at it from a machine learning perspective, that's the dice score, and from a material science perspective, that would be the grain boundary scores. Or the grain measurement scores, direct grain measurements. And here we can see the examples of some of those images: original, gradient, manual threshold, HED, and manual segmentation. So now let's look at the dice scores for the different units, and we can see all of the different training sets. They all scored around 92%. The highest was, oddly enough, training set 10, but it's very close to training set 1, and training set 1 was trained entirely on manual segmentation of the grains, so that would be expected that it should perform the best. All of them are kind of in a similar range here, so let me quickly show the training set data again to refresh your memory. Let's go back to that slide. Okay, so here's that. Training set 1, 2, 3, and 4, and 5. 5 is entirely artificial data. And then 4, 3, and 2 are increasing percentages of artificial data. 25 to 75, 50-50, 75 to 25. And then 6 through 10 are all just different amounts. These ones have artificial data in it, and these ones have noise as well from the different traditional methods. And the training set 10 had noise from each of the different traditional methods. So let's go back to the dice scores. And we can see training set 5 did score the lowest, but it is still an impressive score because it was trained entirely on artificial data. It did not actually see any grain images. It only saw Voronoi Tessalation images. So it's impressive that it was able to score above, well above all the traditional methods, and within range of all of this data, which was trained on actual grain images. These 6 through 10 had different amounts of noise from traditional methods, and then 25% artificial, 50% artificial, and 75% artificial for 2, 3, and 4. So it's an interesting that these all are in the same range, and then there's a slight drop off when it goes to 100% artificial, but not that much of a drop off. So there's definitely promise to using this Voronoi Tessalation grain generation method. Now we can look at some of the grain dimensional measurements. I do want to get a better way of displaying this for the paper. I'm not sure how I'm going to do that yet, but we can see that the measurements are listed here at the bottom: average circularity, max diameter, the line intercept methods, grain individual error, total grains in all 480 images, and we can see how well each of the different approaches performed. Up here we have manual segmentation getting a perfect score because it is our ground truth. Manual threshold, gradient-based approach, and HED method are the traditional approaches shown in the beginning. And gradient-based probably does the worst, under-predicting across the board. HED method did pretty well as far as the grain measurements go, but the machine learning-based approaches did outperform it, especially for 1 through 4. It starts to get away a little bit when we get to the completely artificial data, the Voronoi Tessalation method, but it still scores pretty reasonably across the board. And the noise methods, when we implement some of the noise generated from the traditional methods, 6 through 10, those scores are listed here as well. So now let's just go through some qualitative data. This is UNet training set 3. This is 50% manual segmentation, 50% Voronoi Tessalation data. UNet trained on that. We can see image 1 here is Voronoi Tessalation with added noise. Here's the original mask, and here's the prediction from the UNet, pretty close. And now let's look at the original grain boundary image of stainless steel from our data set, the manual segmentation of the mask, and the UNet's prediction of that. And you can see how similar these predictions are, and it's quite fascinating that it was able to do such a good job with that. It almost thought this was a grain boundary, didn't completely get that closed off. And then here, it's kind of finding a grain boundary there that we did not indicate as a grain boundary. It could potentially, sometimes it's difficult to say what is and what is not a grain boundary. But the similarity between these images is very fascinating. Next, we have UNet training set 5 prediction examples. Here we have the grain with the mask prediction overlay, and here we have it without the background. Here we have it with manual segmentation, and here we have it with manual segmentation without the background. So training set 5 was trained entirely on artificially generated data using the Voronoi Tessalation pattern, and you can see how close it was able to predict this manual segmentation versus the neural network's guess at it, and it never trained on any actual grain data. So that's fascinating that it performed so well. Here is UNet training set 5 on a different image of stainless steel from an entirely different data set, and here is another different image of stainless steel from an entirely different data set. I believe this one, image 6, is SLS stainless steel, and this one is just a standard cold cast of stainless steel. And fascinating how capable this artificial data generation method was able at training a neural network to perform these tasks. I believe that the future, I don't know if I have a conclusion slide or not. No, I don't. So I think the future will be a combination of artificially generated grains on a wide array of grains with manual segmentation, and if you use that combination, then you could develop a very robust neural network at just standard prediction of grains, and it would be able to do this across different metallic materials, and I think that's the future of this science. Thank you to Nanhini Raju, Milos Kursmanovic, and Hossein Ibrahimi for helping me with this work. Thank you to Ramesh from Siemens, Dr. Kapat, and Dr. Ghosh. And if you have any questions on this work, please just leave them in the comments below. Thank you for watching.